Good morning, ladies and gentlemen. My topic of presentation is the use of digital image technique to study leachate penetration in biocemented residual soil. Biocementation is a new soil improvement technique that is environmentally friendly, sustainable, and cost-effective. Various methods could be used to achieve biocementation: ureolysis, denitrification, photosynthesis, sulfate reduction, but the most efficient one is through urea hydrolysis, which is the decomposition of urea into carbonate and ammonium ion. In the presence of calcium ion, the carbonate will react with the calcium ion to form calcium carbonate that will serve as calcite to improve engineering properties of the soil. The two methods by which ureolysis could be accomplished are either through MICP or through EICP. MICP involves the use of live bacteria, while EICP involves the use of bioproduct, which is free urease enzyme. In this study, EICP was employed to improve permeability of compacted residual soil, and digital image technique was adopted to study the leachate penetration pattern and also to determine permeabilities. Materials and method. The materials used are soil and EICP solution. The soil is natural and classified as sandy silt of high plasticity, while the EICP solution consists of urea, calcium ion, and urease enzyme. And the EICP solution was prepared at three different concentrations: 0, 0.5, and 1.0 molar. Methodology. First of all, physical and engineering properties of the natural soil was determined. Then the soil was treated via EICP method through mixed and compaction. The soil was mixed with EICP solution prepared and compacted according to British Standard Light compaction. Then the samples were cured. After curing, then they were subjected to leachate penetration experiment using DIT technique as shown in figure 2. The cured sample were placed in front of two mirrors, and raw leachate mixed with dye was poured onto it from the top. Then the images of the penetration of the leachate were captured using digital camera for the period of 28 days. After the images were captured, they were processed using SAFA and MATLAB softwares, and the results were obtained. Figure 3 shows the effect of biocementation on the leachate penetration pattern at 7 days. As we can see, the shape is rectangular in the untreated soil, but it is irregular in the EICP treated soils, and we can see the rate of penetration is higher in the untreated soil, while it is lower and reduces with the increase in concentration of cementation solution in the EICP treated soils. This is due to the formation of calcium carbonate in the treated soils, and the calcium carbonate will cement the soil and also will block the pores inside the soil matrix. Figure 3 shows the variation of permeability with testing period for the three samples, that is the untreated, 0.5 and 1.0 molar EICP treated soil. As we can see in figure 3, irrespective of the concentration of cementation solutions, the values of permeability decreased with testing period from 0 to 28 days. And regardless of testing period, K value was always highest in the untreated soil and lowest in the 1.0 molar EICP treated soil. It can be deduced that EICP treatment resulted in a significant reduction in hydraulic conductivity by 28% and by 41% in 0.5 and 1.0 molar EICP treated soil respectively. This result obtained in this study conforms with the findings in literature as quoted. Conclusion: the finding has shown that due to the EICP treatment effect, the leachate penetration rate was slower with the increase in concentration of EICP solution compared with the untreated soil, and the reduction in hydraulic conductivity was higher in 1.0 molar than in 0.5 molar. The references were quoted and the abstract were also seen from the left. Thank you for listening. Remain blessed.